Well, good evening, students. It is Mr. Rich. It is Sunday night, 9 o'clock. Tomorrow is the day for AP Calc. I know it maybe is not the most convenient thing to be doing a 9 o'clock live stream the night before your AP exam, but nonetheless, here we are. I'm going to do it. I'm going to jump right in. And my task tonight is to work through these two FRQs that don't think that they're really all that super challenging, but they do give you a flavor of all of the units of the whole class. These are two FRQs that were designed by Bryan Passwater, and he designed these in preparation for the AP exam back in 2020 during COVID, because the exam was a little bit different that year because the students were taking it at home. And so I don't know if he had some inside information or he knew what the exam was going to look like. So he came up with these, I think, are pretty ingenious FRQs that really tested the students on the whole entire class for the whole 8 units. So I thought it'd be a good idea maybe just to revisit these and work these together. Anyway, so this is the first problem. There's 2 problems, and then they kind of branch off into about 6 or 7 different parts. So I'm going to do my best to explain these and teach them as we go. And again, if you don't know who I am Mr. Rich. I am a math coach here in Jacksonville, Florida. I was a math teacher at Stanton College Prep and taught AP Stats and AP Calc there for about 7 years. And now I do full-time coaching of high school math and ACT and SAT math. And if you've got any questions as we go through this, post them in the comments in YouTube. I will be keeping an eye out for those. I did a live stream at 7 o'clock for the pre-calc students, and they were pretty sharp. I made a few mistakes along the way, and they were sure to point them out to me, and I was able to see those over in the comment section. All right, these questions are not going to require the use of a calculator as far as I remember, and if we do, I have Desmos pulled up. Hopefully you have given some consideration as to whether on the calculator portion of your test tomorrow you're going to use Desmos or the TI-84. Use whichever one you're most comfortable with, but I definitely think that when it comes to graphing and solving things with graphing methods, definitely the TI-84, excuse me, the Desmos is the way to go, but out of just convenience and speed. So that is that. I've worked some FRQs here on this YouTube channel over the last few weeks if you want to take a look at those. Well, here is the first question. It says, let G be the function defined by G of X equals this. So we've got a piecewise function that they don't tell us what F is, except they're telling us what F is above. So it's F of X squared minus 5, where X is less than or equal to 3, and then it's a linear function when X is greater than 3. So keep in mind, I'm not even looking at this graph up here is not G. It's not even F, right? It's F prime. Okay, so we'll see how this all unfolds. But it does tell us some things about the function F. It says that it is twice differentiable on the closed interval from -2 to 10. And it satisfies F of 6 equals -4. So it does give us one point that does exist on function F. The graph of F prime, the derivative of F, is shown above. The graph of F prime has horizontal tangents at 2, 5, that makes sense, and 8, and at 9, right? So this is at X equals 8 and X equals 9 right there. The areas of the regions between the graph of F prime and the X-axis are labeled in the figure. All right, it says here, it says, show that G is continuous at X equals 3. Well, if you're going to show that a function, a piecewise function, or any function is continuous, you need to use limits, right? So that's maybe one of the biggest point deductions that students would get on this is if they don't use limits. So what we have to do is show that the limit as X approaches 3 of G of X exists, okay, and that it is equal to G of 3. Right? That's what's going to determine that the function is continuous if that equation is true. Well, this is the big thing right here is I have to determine whether the limit exists. And for the limit to exist, I have to look at what the limit is coming in from the left and the right. So what I'm going to do is I'm going to determine what the limit is from the left. So from the left, this is my g of x. I have to find out what is through substitution. I'm going to do this with substitution. I need to know what g of 3 is. Well, that's going to be f of 3 squared minus 5. 9 minus 5, f of 4. Okay, now, do we know what f of 4 is, right? Because g is f of 4. Okay, and we don't necessarily know what that is. Okay, let's do the limit of g of x as we come in from the right at 3. Okay, but when we're coming in from the right of 3, we're going to be using this. This is going to be 5 minus 2 times 3. So that's going to be a negative 1. Now, they are telling me that g is continuous, right? They're not saying determine if it is. They're saying show it. So this f of 4 is going to have to be a negative 1. Now, so let's see how we are going to determine this, what it is. Yeah. So the only way that we could determine what f of 4 is to use this right here and then include the fact that the area right here is 3, right? So let me show you what I mean. I don't see any other way to do this other than to say the following. If I want to know what f of 4 is, I'm going to take f of 6 and then I'm going to integrate from 6 to 4 of the derivative. Like that. Now, what does that mean? Well, f of 6 we know is negative 4. Now, what's the derivative from 6 to 4? Well, from 6 to 4, the area here is 3. So that means I would add 3 because I'm taking the antiderivative backwards. So therefore, this area which is below would actually count as positive area. And so that would be plus 3. So it's actually equal to negative 1. So that shows that that the limit does exist. And of course, g of 3 is going to be the same value as this right here. So we can say, so therefore, the limit as x approaches 3 of g of x exists, and the limit as x approaches 3 of g of 3 is equal to negative 1, which is equal to g of 3. So g of x is continuous at x equals 3. Okay, any questions on that? What's up, Swipes? Swipes is here. Okay. Questions, class, on that? That was a bit of a curveball, right there, where we had to resort to using our fundamental theorem right here to start at a known value of my function and then integrate to another value and get the change using the integral. So negative 4 plus 3, negative 1. All right, let's go down to the next question. B says, find the absolute maximum value of f on the interval negative 2 to 10. Well, if this is what we would call a candidate's test, right? This is wanting me to find the absolute maximum value over a closed interval. So what we're going to say here is that because f is twice differentiable, because f is twice differentiable, it is continuous. So an absolute maximum will exist. Now, the candidates are going to be at the two endpoints. So we're going to make a list of our candidates, and we are going to put in our two endpoints. But then what we have to do is we have to find the other candidates from -2 to 10, and those are going to be where the derivative, those are going to be at our critical values. So we're going to be setting the derivative equal to 0 and finding the other x values that we need to throw in right here to our list of candidates. So where I'm looking at the f prime function, and so we are going to include 0, 4, 6, and 9, because that is where our derivative is 0. So all of those. Now, what we're going to do here, this is not going to be as bad maybe as we think, because we are going to be able to just use our areas here. So we are going to start at what we did already figure out up here, is that f of 4 is -1. So we already know that at 4, f is -1. So if we go over to 6, we're taking 3 away, but they already told us that, right? We knew that that was -4. So we knew that this was -4. Okay, and then if we go over and integrate over to 9, from 6 to 9, we're adding 7, so that gives me a value of 3. If we go from 4 back to 0, that's 11, but since we're integrating backwards here, then we have to take that away. So that's going to be a -12 right here. Okay. Oh, and if we want to get to 10, we have to go from this 3, from f of 9, which was 3, and we have to add that area 4. So that's going to give me 7. And then going back to 2, I would add 5 to the 0. So that would put me at -7. Okay, so we start at -7. We add 5, that gets us to, it would have helped if I put these in order, but at 0 we get to -12, and then to get to 4 we're adding 11 to -1, and then we are taking 3 away, that puts us at -4. We're adding 7, that puts us at 3, and then we're adding 4 to put us at 7. So the maximum value here is going to be 7 right there. Why do you need the value of f of x is what Swipes is saying. Yeah, because we're trying to find the maximum value of f. And so we're using our derivative and our knowledge of the areas of the derivative function to find out what our function is at these different x values. So we can say here conclusively that the absolute maximum value of f of x over the interval -2 to 10 is 7 at x equals 10. Okay, students? All right, there we go. Let's move on. Part C says for x not 3, the function k, so they're throwing another function at us, k of x. And that looks like a monstrosity, but it is an integral of f prime, partially here, and then -4x, and then some other function that's also a function of f of x down here. But it says that it is known that if you were to evaluate the limit of this function k as x approaches 3, you could evaluate it using L'Hopital's rule. Find f of 3 and evaluate then k of x as x goes to 3. All right. So if this could be evaluated, using L'Hopital's rule, that must mean that if you were to plug in 3 for k of x, that we would get 0 over 0. So what we're going to do is we are going to take the derivative. All right, we're going to take the derivative of the top and bottom. So what we're going to do is we're going to say that the limit as x approaches 3 of k of x using L'Hopital's rule must be the following. Well, if we take the derivative of this right here, well, what's going to happen is we are going to negate the antiderivative, and the 3x will be put into the dummy variable t. So I will have the 3 here, but then this will be 3 times f prime of 3x. But then I have to multiply that by the derivative of 3x, 3. So I'm just going to put parentheses 3 right there. And then the derivative of the 4x, the negative 4x would be negative 4. So that's the derivative of the top. The derivative on the bottom is going to be, the derivative of this exponential is going to be 3 times e, it is itself, right? 3e to the 2 times f of x plus 5, but then times the derivative of the exponent. So that's going to be 2 f prime of x, and then the derivative of the 5 is 0. So we're multiplying that by that, and then minus 1 right there. Now, it wants us to find f of 3, which is interesting. So we know up here f prime of 3, which is interesting. They tell us what that is, but let's see where we go from here. Now that we have taken the derivative of the top and bottom by L'Hopital's rule, we can then do direct substitution once again. Okay. All right. Terrible. Okay. Okay. All right. So now we're going to do direct substitution here. So we're going to do 3 times f prime of 9. And let's do 3 times 3. So we'll put the 9 in the front. 9 times f prime of 9 minus 4. Then this is going to be 3e to the 2 times f of 3 plus 5 times 2 times f prime of 3. Okay, and then minus 1. So it looks like what we do have to do is we do need to find f of 3 right here. Now, f prime of 9, we have that. That's going to be 0. Right? That was a 9 right there. So that's a 0. So that leaves us negative 4 on the top. F prime of 3, we have a 3.5. So this is going to, so we still need to know what f of 3 is. Find f of 3. So we are going to have to figure out what f of 3 is. And can we figure f of 3? Can we do that? There has to be a way to get f of 3. And I don't see it right offhand, even though I know f prime is 3.5. Because we can't really evaluate that. All right, if anybody sees a way to get f of 3. I'm looking. And we had f of, we had f of 4. Yeah, I think I'm going to come back to that one because I don't see, because it does look like we're going to have to get f of 3 to continue to get the limit of this. I think there is a trick to this, though. The limit, k of x goes to 3. Let's move on. Let's go down to part D. Okay, so this one says let h of x be a function such that dy dx is equal to this. So they're giving us the derivative of h of x. And they're telling us that y is greater than 1/3. Now it wants us to find the second derivative and then use that expression to determine the graph, if the graph of h of x is concave up or down at h1 of 2. So we are going to have to take the derivative of this. So let's take the second, the derivative of the derivative here. So that would be, so we'll say d squared y dx squared is equal to. Now we'll have to use the product rule. Okay, so H.G. Shaw was saying, so where did the 3x come from with your derivative? Let's go back up here. This derivative. Yeah, so you are, I guess you're wondering about this 3x right here. Well, that came from the fact that when I take the derivative of the integral, the upper limit 3x is going in for the dummy variable right there. So it becomes f of 3, f prime of 3x. Yeah, so that's where that comes from, which then means that when I put the 3 in, it becomes f prime of 9. I assume that that's what you're asking there, HG. Let me know if it's not. Okay, so over here, when we take the derivative, this is going to require us to use the product rule. So we'll take the derivative of the first, which would be f double prime of 2x times the derivative of the inside, which is 2, but then I would multiply by the second, plus the first, f prime of 2x, times the derivative of the second. Well, the derivative of 3 minus 3y minus 1 would be just the number 3, but then times the derivative of y, which is dy dx. So that becomes our derivative there. Okay. Second derivative test. Yeah, I'm not sure what you mean there, Swipes. Second derivative test. But at any rate, what I'm going to do here is now I need to, that is going to be my second derivative, but I do need to put in the dy dx back over here. So that's going to be, this part right here is going to be substituted in for that. Now it does want me to find d squared y dx squared. So I am going to rewrite this times 2, 3y minus 1, and then I am going to say f prime of 2x times 3, and then we will put in again f prime of 2x times 3y minus 1. So we're going to go ahead and substitute in the dy dx here for a full expression. Okay, so now they're telling us that this function that we don't know, we do know one of its points is at x at the ordered pair 1, 2. So we are going to evaluate the second derivative now at that point. So we will evaluate it at 1, 2. So that's going to be f double prime of 2 times 2. Y is 2, right? So that's going to be times 5. 3 times 2 minus 1. That'll be f prime of 2, like this. And then this is going to be 3 times another f prime of 2 times 3 times 2 minus 1, which is going to be 5. All right, so we're still trying to evaluate this because we want to know whether it's concave up or down. So we want to know whether we're going to get a positive or a negative value here. So if we go back up and we look at f prime of 2, we see that the answer here is 5. So we can grab that. So we still need to know f double prime of 2, but that's going to be 10. F prime of 2 is 5. 5 times 3 is 15. 15 times 5, I believe, is going to give me a 75. And then we have, but we know what F prime of 2 is, right? F prime of 2 was 5. So that's a large number there, right? So that's going to be 5 times 3 times 25. So I got 5 times 5 times 5, 125 times 3, 375. So the only thing that I don't know is F double prime of 2. So we don't have F double prime of 2. And let's go back up and see where we would know what that is. Okay, so we do know F double prime of 2, because since this is a horizontal tangent line, so F double prime of 2 is going to be a 0. So we're reading that off of the graph. So that means that F double prime of 2 is 0. So we are getting 375. So our conclusion is going to be that this is going to be, h of x is going to be concave up at this point because the second derivative is positive. So we had to use our F prime graph multiple times to get the values that we needed to plug in there. So kind of a, isn't F double prime of 2 0? Yes, exactly. F double prime of 2 is 0 because it reaches a relative max. F prime reaches a relative max. So it is going to knock that term out right there. Okay, one more part to this. Part E says, consider the function y equals h of x from part D. For -1 to 5, on what intervals is the function h of x increasing? Give a reason for your answer. All right, so what intervals, on what intervals is it increasing? Okay, so what we would want to do is set the derivative equal to 0. So the key here is going to find the critical values. So what we want to do is take the dy dx and set that equal to 0 and solve it and find those values. So we want to know when is f prime, so it's f prime of 2x, and then that was multiplied by 3y minus 1. So we're setting that equal to 0. So then what we would do is set the f prime of 2x equal to 0, and we'll set the 3y minus 1 equal to 0. Now, when is f prime of 2x going to be 0? Well, I think what we want to do here is actually use the second derivative test, right? Because although we're looking for critical values here, from -1 to 5, we're only going from -1 to 5. On what intervals would the h of x be increasing? So let's see what we want to do here. So we have its derivative and we have its second derivative. That is, let's see. So what are we doing on that one? Let's see. Trying to find out when the function is increasing. This is going to be when y is a third, but I'm not sure that that's going to, yeah, where y is great. So let's see, where y is greater than 1/3. So that's why they're telling us y is greater than 1/3. So that's not going to yield any of our critical values then. And so when would f prime of 2x be 0? F prime of 2x be 0. F of x. I'm not sure about that one. If it's a car for you, cooked. No, that one I do remember. This one that was a tough problem right there. But let's come back. We'll keep moving on. I want to go to the second one here. This one involves a table of values, and we're going to do some approximations here. Let's go back here. Where'd we go? There we go. So this says a large pizza chain delivers pizzas nightly from 6 p.m. to 2 a.m. On a Friday night, the rate that the pizza chain receives calls for delivery is modeled by the different function C prime of t, measured in hundreds of calls per hour, and t is measured in hours since 6 p.m. Selected values of C prime of t are given in the table. Use the data in the table to approximate C double prime of 7. Using correct units, interpret the meaning of C double prime of 7 in the context of the problem. So we're going to use these two ordered pairs right here and get the average rate of change between those. So what we're going to do is we're going to say that C double prime of 7 is going to be approximately, and then we will take the average rate of change there. So we'll take C prime of 8 minus C prime of 6, and then divide that by 8 minus 6. So C prime of 8 is 0.2 minus 1 all over 2. So that's going to give us negative 0.8 over 2, negative 0.4. Now that's going to be calls per hour per hour. All right, that's what the units are going to be here, because the C prime is calls per hour and we're dividing it by hours. So that's going to be calls per hour, or calls per hour squared. Now, it says using correct units, interpret the meaning of that in the context of this problem. So what we want to do is make reference to the interval that we're using. So we would say between, and we can just use t equals 6, between t equals 6 and t equals 8. Yeah, so we can say, well, they want C double prime of 7. So let's say, we'll say this. At t equals 7, the rate at which the chain receives calls is decreasing at approximately 0.4 calls per hour per hour. So the rate is what is decreasing, right? So we're saying that the rate at which they are receiving the calls is decreasing at approximately 0.4 calls per hour per hour. So it's a negative, and that's why I'm using the word decreasing. And then when I put my number, I'm not putting a negative in front of it. Okay, let's move on. Part B. Do the data in the table support the conclusion that there is a time t between 0 and 8 at which the pizza chain receives 300 delivery calls per hour? And by the way, up here, this is not totally right, because this is going to be, we want to put this as hundreds of calls, right? So we would put this at, we could call this negative 40 calls per hour, because it's hundreds of calls per hour. So over here, right, we would say approximate is decreasing at approximately 40 calls per hour because of the fact that it's in hundreds of calls. All right, and then what we're looking at here is 300 delivery calls per hour. Well, you can see that just if you take these two endpoints, 0 and 8, 5 and 0.2, you could just use that as your interval and say that since this function would be continuous, right, it's modeled by a differentiable function. So we would say that because C prime of t is differentiable, it is continuous. And therefore, by the intermediate value theorem, because C of 8, so we're going from 5, so let's do it this way. What we're going to say is that C prime of 8 And in between is 3, right? We're looking for 300, right? So C prime of 8 is, let's see, yeah, is less than 3 is less than C prime of 0. So there has to be at least one value of t over the interval 0 to 8 such that C prime of t is equal to 3, which is 300 delivery calls per hour. So that was an intermediate value theorem problem there. Next, using correct units, explain the meaning of the definite integral of C prime of t dt from 0 to 8 in the context of the problem. Use a right Riemann sum with the 4 subintervals indicated by the data in the table to approximate the value of that. All right, so if we're going to use a Riemann sum, let's go ahead and get the value and then we'll interpret it. So we want to make the following statement on our paper. So we're going to say that this is approximately equal to. And then what we would do is look at what each of these intervals is going to be and use a right Riemann sum. So we have a 1 and a 3 and a 2 and a 2. So on your test on Tuesday or tomorrow, actually, you're going to be looking at this on your computer screen and you'll have scratch paper. I assume how that's going to work. So on your scratch paper, maybe you want to write down those values 1, 3, 2, 2. And then you're going to be using the right edge, right? Because it's a right Riemann sum. So this is going to be equal to 1 times 4.5 plus 3 times the right edge of 2.5 plus 2 times 1 plus 2 times 0.2. Okay, and then we'll add those together. So we have 4.5 plus 7.5 plus 2.4. And so that's going to be, what will that be? 12, 13, 14.4. Okay. Now, what does that represent? Well, remember, doing a dimensional analysis here, right? That is going to be calls per hour, and that's hours. So this is going to be calls, right? So this is going to be summing up what we estimate the calls to be between 0 and 8. So then we would interpret that. We would say this means that between t equals 0 and t equals 8, the approximate number of calls received by the chain is approximately 1,440 calls, right? To be 14.4 hundreds of calls. And so that's what our answer is going to be there. Part D, I think this is our last one here, and then hopefully we have time to get back to those other ones. So here it says that the total number of calls that the pizza chain receives for delivery on Friday night in hundreds of calls can be modeled by this function. Okay, so this is yeah, okay. Calls. Hundreds of calls can be modeled with function f, where x is the number of delivery drivers, right? So here they're making it a function of the number of drivers that they have. When there are 60 drivers, the number of drivers is decreasing at a rate of 7/24 drivers per hour. According to this model, what is the rate of change of total delivery calls with respect to time in hundreds of pizzas per hour at the time when there are 60 drivers delivering pizzas? So they're asking us to find df dt, right? Because f is the it's the number of calls, hundreds of calls, but they want us to get the rate of change of the delivery calls with respect to time in hundreds of pizzas per hour. Okay, delivery calls with respect to time in hundreds of pizzas at the time. All right, so what we have to do is we do have to take the derivative of f of x, but with respect to time. So we're going to have to use the quotient rule and use the chain rule because we're going to be doing the derivative with respect to time. So that will mean that we are going to do low. So we'll do 200 minus 2x, the derivative of the high, which is 2x times dx dt. Since we're taking the derivative with respect to time, every time I take the derivative of x, I will be putting in a dx dt. And then minus, right? So that was low d high minus high x squared times the derivative of low, which would be minus 2 times dx dt. And on the bottom, that's just going to be 200 minus 2x to the second power. All right, so that is our derivative of f with respect to time. And x is the number of delivery drivers. So we know what we're plugging in. Our x is going to be 60. I assume they picked this 7/24 rate, and that's a decreasing rate. So we got to put a negative in for dx dt. But I assume that's going to make the math easy. We are about to find out. All right, so let's evaluate df dt when x is equal to 60, when we've got 60 drivers. So that's going to be 200 minus 120. 2 times x, that's going to be times 120. My dx dt is 7/24. Okay, minus x squared, so we're going to do 60 squared. So let's call it 3,600. Times -2. And then times 7/24. All right, and then down here, this is going to be 200 minus 120. That's going to be 80 squared. So now I'm thinking that this has got to be a calculator active right here. There's no way that that's going to be something that they would want you on a regular. Remember, this was during COVID, and I think that they assume that you're using your calculator here. So if we were to do this on the calculator, let's try it and see what happens here. So that is going to be 80, 120, and now we're going to put in 7/24 up here, and minus 3,600 times -2 times 7/24. All right, now I'm going to put this all in one big parentheses so that I can come here and then put that down in the denominator, and that's going to be 80 squared. Okay, so I get that number right there. I get a 0.765. Now, let me see if I have the answer here. I think I do have it somewhere. And we'll check to see if this is for real. They don't give us the answer on it. So yeah, I don't have the answer on it. Okay, but let's check it and just make sure that we got all of this right here. So 80, 200 minus 120, and then we've got the 120, which was the 2 times x. Oh, okay, one of the things that we missed here, -7/24, right? Because the rate was a negative. I knew I was going to forget that. So that's a negative right there. Okay, so what that does is that changes it then to nets out to be a negative 0.766. 0.766. So then the rate of change of the total delivery calls with respect to time in hundreds of pizzas per hour. So that is going to be, I think they meant calls per hour, right? That doesn't make sense that it would be the rate of change of the delivery calls. It should be calls per hour. That seems like that's an error, but it'll be negative 0.766 as our final answer there. All right, now let's see if I've got answers also or anything on the first ones here. Yeah, let's go back up and see where we left off here. Yeah, so we got stuck on that one, and yeah, on this one, because we were trying to find f of 3. And there was a, I seem to remember there was some kind of a twist for us to find f of 3. That just didn't, it wasn't obvious at the time when we worked this. F of 3, because we've got the derivative there. There was something about this problem that allowed us to find f of 3. And I don't know if it was in here. I think it was. It would have to be. It would have to be the fact that this is 0. Because if you were using L'Hopital's rule, you would have had to have 0 there when x is 3. So if you were to take that limit, what we know is that the limit of 3e to the 2 f of x plus 5 minus x, the limit as x approaches 3, that had to be equal to 0. I think that's how we were finding f of 3. Yeah, because what would happen here, for that to be, when we plug 3 in, we get 3 times e to the 2 times f of 3 plus 5 minus 3 equals 0, like that. And then if we solve this for f of 3, we get, we move the 3 over and we divide by 3. So we get 2e raised to the 2 f of 3 plus 5 is equal to 1, like that. And that's adding the 3 and dividing by 3. So then if you were to take the natural log on both sides, you get 2 times f of 3 plus 5 is equal to 0, right? Because the natural log of 1 would be 0. So this does allow you to calculate f of 3. So f of 3 is a negative 5/2. So that's what was going on right there. So they wanted you to do this, set the denominator equal to 0 by recognizing that the limit, if L'Hopital's rule had applied, then the limit as x approached 3 of the denominator would make it 0. So then actually, then at that point, we are able to proceed, because we didn't know what this was down here. So now we knew that we had negative 4 on the top, and this would be 3 times e, and this would be f of 3 is a negative 5/2. So that's e to the negative 5 plus 5. Right? You see that? If that right there is what was equal to 0 right here. So you have 3 times e to the 0, and then that was times 2 times f prime of 3. And f prime of 3 was 3.5, back from the graph up there. So that makes this times 2 times 5 over 2, and then minus 1. So that turns out to be negative 4. That's going to be 14, right? That's going to be 3 times 1 times 2, 6. 3, 15. Yeah, it's going to be 14. So that's going to be a negative 2/7 is what our final answer is going to be there for the limit of k of x as x approaches 3. All right, so we got that one knocked out. And then, yeah, we were good on that one. And yeah, but this one was the one, I think, also. Yeah, and what intervals is the function h of x increasing? So we're back up here at this h of x. We want to know when the function is going to be increasing. And it looks like we got one of our, we're trying to find one of our critical values. When is f prime of 2x equal to 0? Did we find that out? When would f prime of 2x be 0? Yeah, that's the one that I kind of get totally stuck on here. Yeah, let me see if there was any hint on here. They, on the answer key they handed out to us, it has very little information here on part E. No, but there was a part F too on this. There was a part F. I don't think I copied it down here, but there was a part F. Yeah, part E, it just says correct intervals with reasoning. Yeah, I'm kind of at a loss on that one. It just doesn't come back to my mind. However, I do want to go grab part F on this, because I think I have a part F that I did not bring over. Yeah, there's a differential equation part to this, and I got 5 minutes left, so I think I might be able to get this one in. Let's see. Let's paste that one right there. So this says, consider the differential equation from part D. Use separation of variables to find a general solution of the form natural log of 3y minus 1 equals a times f of b. Okay, so we need to go back up to part D. Yeah, and we want to get this one. So let's see if we can knock this one out. So let's just grab this. And we'll bring it down here. All right, so they want us to use separation of variables. So if we're going to use separation of variables here, we do have to divide the 3y minus 1 to the left side. So it'll be dy over 3y minus 1. And then this will be f prime of 2x dx. And then we will integrate both sides. Okay, so when we integrate over here, we are going to get, by u substitution, we'll have 1/2 f of 2x plus c. Right there. And then over here, this is going to be, this will be 1/3 natural log of 3y minus 1. Absolute value 3y minus 1. So remember, you're using u substitution here, but as long as this is a linear function down here, we just know that through u sub, it's going to put a 1/3 coefficient. If you're not sure about that, you can do that and say, okay, let u equal 3y minus 1. du ends up being 3 dy, and then that gives you dy is equal to 1/3 du. So when you replace this dy, you're putting in a 1/3 multiplier, and it becomes then du over u, which is natural log of u. So anyway, so that's what you get right there. All right. Now, what they want us to do is they want us to, I think that's it. I think, what was, they want us to finish it up. Yeah, they just want us to get to that point right there. So we need to move the 1/3 to the other side. So I'm going to multiply 3 on both sides. They didn't really, I guess for time's sake, they didn't want us to go any further with this. So we have that. That's going to make this 3/2 f of 2x. And don't forget, when you multiply it by 3 times c is just another c, right? So we're still going to just use that as c. And that takes you really to the final answer for that problem. That's as far as they wanted you to go right there. All right, everybody. That's going to be a wrap for tonight. Apologies that we couldn't finish the next to last problem there. E, I'll try to find out the solution there and then maybe post something in the comments section. But I do thank you for joining us. I do wish you all the best of luck tomorrow morning at your exam. Be sure to take your calculator with you and have your device charged if you have to use your own device at the school. So be plugging that in tonight. And I do have a live stream that I do just about once a week. So I post those in advance. So if you subscribe to the YouTube channel, you'll get notified of that. And I do tutoring for all levels of math. I do all the way from Algebra 1 up through AP Calc. And I do AP, or I should say ACT and SAT math prep as well. All right, everybody. Have a great week ahead and good luck on your AP exams this week. Good night, everybody.